One thing people wonder about is whether or not they should get a structural engineer to design their retrofit and then give that to a contractor to implement the retrofit. What we've discovered is that many engineers do not have the experience or expertise needed to design an effective retrofit. The reason for this are many. One is there's no retrofit building code for this, so they literally can make things up in terms of figuring out how a house is going to react in an earthquake. In order to decide these things, you need to do some research. You need to look at existing building codes from old building codes from before. You need to look at damage photos from previous earthquakes. And hopefully you've been someone like me who worked for the Federal Emergency Management Agency and seen this damage for yourself. So you need to be careful with your engineer because you may hire an engineer simply to find out you cannot afford the design. This usually happens when an engineer is not familiar with existing building codes, with old building codes, with the way houses have failed in previous earthquakes, and they literally make things up. Shortly you will see some samples of that, and these things can be very expensive. I've seen many engineers recommend foundation work when tests on old foundation prove that was not necessary. I've seen samples, which you will also see shortly, where they were recommending procedures which had absolutely no basis on any proof that it was ever a failure point. So all of these things are very important to consider when you're looking for an engineer. Now that's not to say engineers don't have that skill. Some definitely do have that skill, but you really want to be careful about who you hire. You will also want to know if they understand practicality. For this, go to the Finding a Contractor webpage, shown here, and see if your engineer can answer those questions. I've met engineers that didn't even know what a hammer was. Or you can find a contractor who understands the engineering. Personally, I think finding a contractor who understands the engineering is better because he'll understand the engineering, and when he gets underneath a house and he sees something, he'll know exactly what to do. And a really good way to find out about the quality of an engineer is to contact members of the American Society of Home Inspectors, because they look at these retrofits all the time, and you can find a good contractor that way, and you can also find a good engineer that way. So for example, they may have looked at a house that was designed by a certain engineer. They go in, they look at it and go, yeah, this guy did a really good job. And that's the sort of engineer you want to look for. So I'd like to discuss something here. These are posts underneath the house in the middle of the floor. Here's the floor you walk on. The perimeter foundation is all along the edges. And these posts right here help support the middle of the floor, and then there's a piece of concrete right here. Now many contractors and engineers retrofit this connection, this post, and I'll show you what they do. So here's our piece of concrete right here. That's called a pier block. Then there's this post right here. And then there's a beam that goes this way, and then that supports the floor joist, and then the floor you walk around on is right up here. So they'll put this piece of steel here and this piece of steel here. Sometimes they'll even put new concrete here. Now this is all a complete waste of money. There have been no damage because of this connection being weak in previous earthquakes. None of the existing seismic retrofit guidelines, of which there are 5, recommend doing anything here. And this is a case of an engineer or contractor making up what they believe is going to be a failure mode. Damage does not occur here. It occurs when the house rocks back and forth, and if the floor above moves, then of course the post will fail, it'll tip over. But if the house doesn't move on the foundation on the outside, you don't have to worry about this. So we'll go over this a little bit more. So this is a T-strap. This is on top of a post. And so again, it's connect that girder or beam to the top of the post. And again, this is a complete waste of money. This is not a failure point. This just doesn't happen. So there's no reason to spend money on this. If a contractor or engineer says they're going to do this, you may really question if they have the kind of education in this subject that you would like to hire. So again, this is another one. Here we have the bottom of a post going into a pier block. Here's a bolt where they bolted it in. And again, this is completely unnecessary, very expensive. So here's an example of a house where the contractor or engineer thought this was so critical that they went and they put in new concrete here, they put new steel right here, they put a piece of steel right here, they put them all together. And this was, again, a complete waste of money. If you take an average house and you decide to follow these procedures, you can end up spending $3,000, $4,000, maybe $5,000 just for this. and get absolutely no benefit. And just to show you what the building code actually says, and it says here, the column shall be, and this column is the same as a post, the column shall be restrained to prevent lateral displacement at the bottom end. Lateral displacement at the bottom end can mean one nail. So the only thing really required, according to the building code, is just a connection of some type, including a nail. Now remember the parts up here at the top, they don't even care if there's any connection at all. It can just be there on gravity. That's how unimportant this connection is. So again, if you're going to hire someone, if they recommend this and you like them in every other way, say, hey, I would just as soon you not do this part, and you will not have compromised your retrofit at all. Now I'd like to show you some engineering details that have been put together for contractors to use. An engineering detail is a drawing that shows a contractor where to put the bolts, where to put the nails, how it should be done. So here we see a drawing, and this is the beam that supports the floor. This is the post. This is the piece of concrete called the pier block. And what this engineer is doing is he's putting this T-strap. We saw a sample of one of them previously. Then there's a piece of steel right here. There's a bolt going through that piece of steel. And then there's some bolts going into the pier block. Again, this is a complete waste of money. And you can imagine how much work that would be, you know, to put in the bolts, get the hardware, drag it underneath the house, etc. This is the exact same thing here. Here we have the T-strap, where we have the post, and down here is where the pier block, the concrete is. Now look at this, it's very, very interesting. This right here, it says connections are not load rated. What that means is they don't have any resistance to earthquakes at all. They're not rated to resist lateral loads generated by earthquakes. So even the manufacturer's catalog tells you that these are a worthless item. Now here's one, this was one that's fairly complex. I want to show you how extreme some contractors and engineers can be. So the first thing this person wants to do is he wants to put in a massive amount of concrete. So this concrete is 18 inches deep, 18 inches wide. You have to dig the hole out. Then you have to drag the concrete into the underneath the house. Sometimes you're going to be dragging it 25 feet. You have to do it a couple of times to get that much concrete. So there's this huge amount of concrete. Then there's reinforcing steel right here, right here, right here. And then there's, you know, these big steel bars that go down it. And then there's another piece of steel right here. Then there's our post. Then there we have a metal connector right here. That's the, you know, the post to beam, top of the post to beam. And then we have a piece of steel right here. So you can imagine how expensive this would be. And if you have 15 posts underneath a house, you can imagine what that would add to the cost. This particular retrofit, when we gave a bid, this was a 1,200 square foot bungalow in El Cerrito. This entire retrofit was going to cost about $70,000 because this particular engineer did this sort of thing all over the house. So that's why you want to be really careful about what your engineering is planning to do, what the design is going to look like, because you might get something you simply can't afford. Another thing they often recommend is blocks that should be put on the mud sills for the shear walls. What that means can be researched further on our website. You just look up the most critical plywood connection. And if you look up the most critical plywood connection, it will talk about the importance of these blocks and why nails should not be used. Here's an engineer who recommended putting these nails in. Here we see it again. This is the block right here, and this means use 12 10-penny nails. 12 nails is guaranteed to split a block that small. 4 nails will split it. So for example, this one right here only had 4 nails and it split. You can imagine what this engineer is recommending here, how it will split it for sure. This is a good example of how an engineer can be stuck in their head. In other words, he'll say, okay, if we put in 4 nails, great. If we can put in 12, then it'll be even better. But he doesn't think about the fact that it can split the wood. In fact, it will split the wood. He's just in the numbers part. So numerically, mathematically, yeah, it would be great. But from a practical point of view, it's completely ridiculous. So next I'd like to talk about a connection we see in many engineered designs. This right here is the floor joist. And you see that at the top of the cripple wall. And then this is the floor that you walk around on. And what they like to do is connect the joist to the subfloor. So right here, this is a piece of steel. It's obviously a bunch of black lines from your point of view, but this is a piece of steel. And so this piece of steel connects a joist to the subfloor. Now the interesting thing about this is, number one, is that's never a failure mode. In other words, in previous earthquakes, no one ever saw a failure like that. So why would you enforce something that doesn't fail? And again, this goes back to the engineer's imagination. They think, well, theoretically, it could fail. If I were to just assume everything is just sitting there by gravity, of course it would fail. Now, if you went to the archaic building codes in the international existing building code, you would find that there's a section there that does talk about this connection and how it is fine as is. This means the connection between the floor joist framing and the floor you walk on can resist 600 pounds of shear force. 600 pounds is 75% as strong as a bolt. Over an entire floor, that's a lot of strength. Augmenting this connection, as recommended by some engineers, is a complete waste of money. But most engineers do not do enough research to discover that sort of thing. So I did do some research on this, and what I found out, if you were to make that connection, okay, right up here, you would need a very short nail. In other words, if you do a nail longer than, an inch and a half, it's going to shoot right through the floor. So what you have to do is you have to use these real short nails, and there's a connection calculator produced by the American Wood Council. And when you look at that length nail and then the type of hardware, what it says is that the penetration into the wood is so small that it can't be rated as having any value at all. So what that means is you can do all this work to put this piece of steel in and get no benefit. So from an engineering point of view, and why engineers recommend something for which you get no engineering benefit is something that you need to ask your engineer if you see this. Okay, I'd like to talk about something called the redundancy factor. And redundancy factor means that the existing connections on a house are already pretty strong. I have to say that when engineers look at houses, they often think that, well, there's nothing there holding it together anyway. So they just assume there's no mud sill to foundation connection, there's no nails in anything, and they just go ahead and start overdoing everything, pretending there was nothing there. It gets really expensive. We need to remember, and this is based on previous earthquakes, that houses do quite well. All those connections are pretty strong as is, as this photograph shows. So you can see this house fell in the Alaska earthquake. I believe that was in 1964. And the glass isn't even broken in the windows. And the shape is just fine. The inside will be messed up for sure. But there's all these connections that are very strong. Sometimes we see engineers recommending that the roof to a wall connection be strengthened. And look how far this house fell. It didn't even come loose. So a lot of these connections, a lot of these things that engineers come up with are not important at all. This is another thing that's recommended by some engineers. This is called an angle iron brace. If you go onto our website and you look up angle irons, I have a whole video on angle irons and how ineffective they often are. You might want to look at that. This is a very interesting story. A few weeks ago, I was contacted by a possible client, and he wanted to hire us to design and install his retrofit. And what he told me was that he had an engineer come over, and that based on the information he had gleaned from our website, he actually knew more than the engineer, and he didn't feel comfortable at all hiring him. So this is to point out that just because someone has an engineering degree does not mean he understands wood frame, seismic, retrofit engineering. That's what you need. So when you interview engineers, you want to ask them, do they have a lot of experience doing wood frame, seismic, retrofit, or at the very least, wood frame? We have wood frame engineers, we have concrete engineers, we have steel engineers, we have some that design skyscrapers, some that design houses, etc. So the one you really want to stick to is wood frame at the very least. I hope the information in this video has helped you understand more about seismic retrofitting and how to protect your own home. We're producing more videos, and if you would like to know when they are available, please click the subscribe button. Thank you.